reaction rate, the way the reaction's going.
Okay. Yep, no problem. So the common ion effect, so we'll like do a quick like general equilibrium review. So remember, equilibrium deals with K, and there's lots of different types of K, Ka, Kb, Kc, Kw, Kp, all those things. And it's always going to be your products over your reactants. That's always the general setup. And so when you go to set these up, if you had an equation, I'll just make that. I'm going to use a KSP problem. And so KSP is going to be solubility. And so that's going to ask about how much of a substance will dissolve in water. And a value that has a really, really small K value is going to mean that it doesn't dissolve very well. It has few products. And then if it has a large, then obviously it dissolves really well, so it has a lot of products. And so if AgCl isn't very soluble in water, so you would expect it to have a pretty small one. I don't remember its KSP value. Instead of looking it up, can I just make it up? Anybody going to be upset about that? Okay, we're just going to make it up. All right, times 10 to the negative 16th, 4 times 10 to the negative 16th. I made that up, internet. I don't know what it is. Go Google it if you want to know. But the idea is AgCl is going to dissolve some. That's a pretty small number, so we know it's not going to dissolve a lot. But when it splits into water, it's going to become Ag plus and Cl minus. And if we just put it in regular water, you can run a regular old equilibrium problem. But that's not what you asked me about. You asked me about common ion effect. So let's say I put AgCl into a solution that already had one of those ions in it. All right. So you would start with, typically, you start your initial values with 0 because you would say you have none of your substance in there. But let's say instead I put it in a 0.1 molar solution of NaCl. Okay? And since it's 0.1 molar of NaCl, that's 0.1 of Na and 0.1 of Cl. The Na doesn't matter to this, but the Cl for sure does. So instead of starting with 0, I'm now going to start with 0.1. And that's really where you have your difference. The rest of your work would end up being the same. So I have no Ag. This is a solid, and that's why I'm ignoring this side. So what's happening here isn't going to affect my overall equilibrium, because remember, you don't include solids or liquids, only things that are aqueous and gas. And so we're going to definitely move forward because we have to make some Ag. So I'm going to add X to this side and add X to this side. And so it ends up being X and 0.1 plus X. The amount of difference that this X is going to make is very, very small. So I'm going to have X times 0.1 plus X. And I'm doing an equilibrium expression. Or maybe I should step back. So if my equilibrium expression is going to be my products over my reactants, since my reactant is a solid, I'm not going to include that in this instance. And my two products are my Ag plus and my Cl minus. And they're going to be equal to 4 times 10 to the negative 6th. There's a very large difference between those two numbers. So X is not going to be noticeable to 0.1. So I just ignored it. And now that gave me 0.1 X equals 4 times 10 to the negative 6th. And so then X is going to tell me how much of my AgCl is actually going to dissolve. That's essentially your common ion effect. And it doesn't have to be with solubility. It could be in any equilibrium problem. It's just kind of the general concept. Does that answer where you were? Okay. So I'm going to move my decimal 0.4. So it becomes 4 times 10 to the negative 17. Okay, Kirsten, you looked like you had potentially a question. I thought you had your hand up. You might not have. Anything else, common ion effect or KSP while it's here?
I remember class like you're going over PKA and P or K. But like we didn't know that was, but
Yeah, I can do that. Welcome. Lauren, there's learning targets in the middle of the table if you want one. Okay, so Le Chatelier's principle. This one that works. It's probably close to the right next, but. All right, so never use Le Chatelier's principle as your explanation for something. You're not going to just say, according to Le Chatelier's principle, your concentration goes up or goes down. Okay, make sure you are explaining it. You can explain what happens, but it's always going to be based on the shift in your reaction. And so what we're saying here is you're starting at equilibrium. So we were already there, and remember at equilibrium, your forward reaction and your reverse reaction are already going back and forth at equal pace, right? So if we do something to our equilibrium that causes a stress or stops it from being in equilibrium, now I'm no longer going back and forth. But the reaction naturally proceeds towards equilibrium, so it's going to shift itself accordingly to get back to the equilibrium position. So a student or a teacher.
nobody.
Door.
Just my door just magically opened on its own. Probably they realized I had a room full of people. Okay, so let's just make up an equation. Is that okay with you guys? Okay, just made up an equation. So Le Chatelier's principle is going to give you a situation in which you have done something to stress the system, and you need to determine what the system will do to relieve that stress. And so there's just so many things. It's not likely that they're going to give you just like, oh, if you increase A, well, now you know that A is going to shift you forward. So you're going to go away from that. They're going to try to give you some harder questions so you can kind of look for what's happening. One of the common things they like to do is take out a substance that's in there. And since you can't just take something out, you have to give something that will react. So let's say we have imaginary compound W, that when you have W plus B, they make a solid, right? So if I add W to my reaction here, it's going to grab out some of this B and stress my reaction by decreasing B. So we were going back and forth, and now all of a sudden I've balanced it so that my B was too small, right? I guess I should write it like this. And so we need to do something to shift so we can start going back and forth. And so my reaction, the reaction will naturally shift to replace what was lost. And so these two here will react, and they are going to form more A and more B. So the amount of A will go up, the amount of B will also increase, and my amount of C and D are going to go down. We call that a reverse reaction or a shift to the left. So there's three things that you're going to have to know that shift your reaction. Concentration being one of them. Increasing it or decreasing it can make a difference. Temperature is another one. We got concentration, temperature, and pressure. Temperature is the only one that can change K. When you change temperature, it's also going to make a difference in K. So let's just make it up here. I don't know. This is fake reaction. So let's imagine that this reaction had a delta H that was greater than 0. If it's greater than 0, what does that tell me about the reaction? Endothermic. And if it's endothermic, what does that tell me about energy? So it tells me that we need energy to begin the reaction, right? Energy is used with the reactants. When those two come together, they use energy. When these two come together, they make energy. That's what that means for it to be endothermic, right? So let's say we were to heat up the reaction. I put it on a hot plate, reaction gets hotter. What have I done to the reaction?
Right.
Okay, because we've increased our heat, right? So I've given more ability for A and B to be able to react. I've given them what they need, and so those two will react. And then they're going to shift to the right or in the forward direction, which increases C and it increases D. So what's that going to do to my K value? Remember, K is products over reactants, right? So if I've now increased my P, my products, and decreased my reactants, then my K value is going to do what? Increase. And one thing to help you just sort of remember is that an endothermic reaction, temperature and K always change the same direction. So if my temperature went up, my K goes up. Let's do it all in reverse. Let's just change everything. So now if my delta H is less than 0, what does that tell me? And so my energy is, and now my energy works with my products. So when energy is available, then C and D are more likely to react, and they'll go that direction. What did you want to talk about if we cooled this reaction down? So if I put this in an ice bath, putting it in an ice bath is going to cause the reaction to cool down. And so when we do that, we've removed the energy that C and D needed to react. That's going to stress it, right? So the reaction is going to do what? It's going to shift right to replace that lost energy. So our reactant amount will go down and our product amount will go up. So what's that going to do to my K value? Products go up and reactants go down. What happens to K? Going to increase. So in an exothermic reaction, they have the opposite effect. You can kind of think about your X as like crossing over. I don't know if that helps or not. But if my energy went down, so my K went up. My energy goes up, my K goes down. Those two I have seen overall. You guys feeling most comfortable with temperature and concentration? I think pressure seems to be the one we have the most trouble with. A safe assumption. How to do a different problem. Yes, sir.
This is like a really quick question.
Go for it.
I always get confused. KC is for solutions and for gases.
You could use KC with anything. KP you could only use with gases. Another thing. All right, I'm going to make a fake thing up too because I can't come up with it. I guess I'll do the same thing I had before. All right, so we've got gases and we've got a solid. Okay, so in this instance, when we're dealing pressures, we need to pay attention to that. Anyway, so when we're dealing with pressures, a couple things you need to consider is, first of all, why does pressure happen? How do we measure pressure? ATM, those are your units. And then that unit, we're able to measure it due to the molecules colliding with the surface, right? And so how often those molecules collide, that's going to determine how much pressure is created. And at equilibrium, you have a given pressure value. Just like anything else, you're reaching that equilibrium. So when you adjust the volume of your container, now it is a smaller space. So if I didn't make any changes, my initial values would have increased my pressure, right? And if this was just a regular gas law problem, that's what would happen. But because we're at equilibrium and the reaction has the ability to shift left or shift right, and it has an equilibrium pressure, it's going to shift accordingly to relieve the stress of this increased pressure. So when we increase the pressure, your reaction will shift to favor whichever side has fewer moles. Because now there will be less moles to run into the surface, and it will help to maintain a similar pressure to what we had at equilibrium. It'll return it to that equilibrium. Make sense? So if we decrease the pressure, now your reaction is going to shift, because once again, it still needs to maintain the pressure, or at least it's going to shift to attempt to maintain the pressure. And so it will favor the side with more moles. So if I gave a situation, let's say we increased the pressure of my reaction here. Which way is my reaction going to shift? If I increase the pressure, it would switch to the left, right? Because I have 3 moles here and 3 moles, or 1 mole here, and that's 4. And I have 2 moles here and 1 here, but this one doesn't count because it's a solid. So I'm only looking at the moles of my gases. So we have 2 moles on this side. Granted, it wouldn't have made a difference because I'd still have 3 and that's still less than 4. But the point being, nonetheless, so if I increase my pressure, I need to favor the side with fewer moles. So that would be my reactant side. So this particular reaction would shift in reverse.
If it's like on a FRQ and it's in like a sealed container and you add more gas, would you consider that increasing concentration or increasing pressure?
What is a gas that reacts, or is it just a random gas? Do you have is this like based on a particular problem? Because if it's going to react with one of those, what it's likely to do is kind of like that very first problem we did, where let's say it reacts with the B and then it would decrease the amount of B that you had. And so it'll cause your reaction to shift. And that would be more like we would think about in a concentration problem if it's reacting with one of your substances. Other questions? Does that cover Le Chatelier enough, or do you want me to do some more practice, or feel comfortable with that? Well, let's see what other questions we have, and we can always come back to it. Anybody else have questions? You have another question? Oh, go for it.
Okay, so we were in our study group and we didn't, do we have another kind of iron on the dipole? How is that stronger than the dipole? Or hydrogen?
Because what you're dealing with, the ion dipole bond, you have, let's say, like Ca+2 and water. Were you doing a multiple choice problem, or were you doing a?
Yeah, it was like which one's stronger, ion dipole, like on this version, like.
Oh, it was just.
Are there a couple where like it gave you like an element or like the compound, and then it asks like which of like the 3 compounds are the strongest, and then the answer would be A because it's iron dipole.
Okay, well, we'll talk about ion dipole for a minute, and I'll see if that's enough to answer your question. And if you've got something more, just ask me, okay? So let's use, for example, a water molecule with a solid dissolving in water, right? So if you had a lattice structure, it's not perfect, but so imagine that we have like our crystal, right? And it's a solid. We drop it into water. Water molecules are going to go and attach themselves to each ion and pull them apart. So we've got a lot of things happening here. You have the bond here is going to break apart, and there's the strength that's in between those 2 bonds. And then you have the bond that's going to happen when this bond's here. So we've got O and H and H. So my oxygen and my calcium will be attracted to there. So let's imagine that that breaks apart and gets surrounded by some oxygen, part of the water molecule. And so when that happens, this is an ion. So those electrons are close to the surface. It's going to be much smaller when you have an ion being attracted to a water molecule. Oh, because I'm just still, sorry. No, I don't know. I don't know why F was -2. It should be -1, I think, because I was putting 2 of them. But anyway, so ion dipole, we're looking at the attraction from this to this, okay? And keep in mind that all of the attractive forces in the whole chemistry world happen all because of our Coulombic forces, which I don't know how to spell. I can never remember. Our Coulombic attractions, right? And so that's going to be based wholeheartedly on 2 things: the distance between your 2 substances and how strong of a charge they have. The strength or the magnitude, right? So calcium, because it's an ion, those protons there in the center of the nucleus are going to be more available. They're going to allow for this to get closer to that water molecule than this water molecule and that water molecule would have been able to do to get together. And so when we go as far as strength goes, ion dipole is going to be one of the strongest types of bonds you're going to see. Then hydrogen. And dipole. Trying to think about what situations. You don't happen to have any, I don't know what they gave you as scenarios. Do you remember?
They like give us like a list of like 3 different compounds or whatever. And
Specific compounds like CO2 and
then it asks us to like rank them in like order least greatest.
what do you remember what the ion dipole bond was that they gave you? Did they give you like a solution of
I think it's like LiOH. That sounds right. It's LI something.
do you have a question?
Can the limited dispersion be like strong in anything if the block is big enough?
That's the true thing. So unless large. And then it gets moved up. Oh, so okay. LiOH. OH here is a polyatomic ion. And so if you remember how polyatomic ions work, they themselves are covalently bonded. So the O and the H together have that covalent bond, which means they have the ability to participate in both an ionic bond and a dipole bond. Yeah, it's fun. And lithium here is an ion. So what they're looking at here when they're looking at the ion dipole bond, that's going to be stronger than your traditional ionic bond because it has both of your covalent bond as well as your ionic bond.
What bonds do polyatomic ions use?
They're covalent. These 2 are bonded together covalently.
You said like you can use like 2 of those or something.
So it's an ion and a dipole.
Okay.
It's polar and ionic. That sounds like, did that come from a review guide, like a practice guide? Yeah, I'm going to say it sounds a little bit more like a ticky-tacky type question than I think I've seen. If you kind of compared it to what you saw in those multiple choice questions, there aren't a lot of things that are just like, do you know that fact about it on the AP test? A lot more times they want you to be able to put things together. So that's still there. Other questions? Is that enough? Did that answer your, does that help? Okay. Like there's this specific topic came up. There was a multiple choice question. That's what I thought you guys were asking me about, where they gave you like a scenario that said delta H was positive, and then it gave you CaF2 was being dissolved in water, and it asked like for which of the situations must be true or something like that. And
It was like question 5 on the
Right.
practice stuff.
Right, and I just can't remember the exact wording, but did you guys remember that question? And so one of the questions, it was like the ions between Ca and F minus were the strongest, or the bonds, the ion dipole.
It like told you the
Was the
delta H
strongest.
like positive, and
Right.
I wanted you to figure like explaining why how to go in water.
Right, something like that. But it had to do with, then what does that tell you about your bonds, right, in the water?
Yeah, it was like when delta H is positive, what does that mean? Like whether like bonds are being formed or bonds are being broken.
Right, I know that's what, but I was trying to remember what the exact wording was. So anyway, and it was like one question that was essentially, was your calcium and your fluorine ion the strongest, or your ion dipole the strongest, which would have been between your calcium and your water. And so because my delta H is positive, if you keep in mind what was happening, is my water, like I said, was breaking apart your ions. So over here, we broke bonds, and when we break bonds apart, are we putting energy in, or are we taking energy out? Yep, energy goes in. And then when we put our ion, Ca+2, here, around those water molecules, now I'm forming some bonds, right? And so when we form bonds, energy goes out. So overall, if I have a delta H that's positive, is more energy going in, or is more energy coming out? More energy is going in. So that means that the bonds that were broken had to be stronger than the bonds that were formed. That's a pretty good, I might have been able to just make it through there, but we can look at it. So the idea here is they were getting at, like, do you understand the concept between breaking bonds and making bonds, and which ones are stronger than and how they relate to delta H? Like, so that type of multiple choice question, I feel like is probably similar to the varsity tutors one you guys are doing, but they're just going to expect you to take it a little bit deeper. Does that help? What other questions? I'll stop talking about that problem. Go for it. Yes. I had a moment where I was thinking of electrolysis, but no, you said hydrolysis. All right, so hydrolysis is a really great thing to talk about because I've seen several questions where they ask that question that we asked you in general chem, and they are going to ask you again in AP, and they expect you to answer it differently than you did in AP. And it'd be like the question of, if I react NaOH and acetic acid, what's my pH? Or is your pH going to be above 7, below 7, at 7, right? And so being able to explain that beyond the fact that this is a strong base and that's a weak acid, so your pH is basic, if you say that, that's not getting you your points on the test. You have to be able to explain that using the concept of hydrolysis. So what's going to happen is this strong base and that weak acid, they're going to react. It's an acid and a base. That's just what they do. When you put them together, they are going to react. So let's say we're at the equivalence point. So they reacted equal amounts. All of my moles of NaOH are gone, and they're going to react with all of the moles of HC2, H3O2. All right? So when that happens, my H here, my OH here reacts. And now I'm left with these two wonderful ions. They have the ability, okay, right? They turn into water. And then the question is, the water that was already there and the water that we've just formed have the chance to react with these. Is it going to? Will the water react with one of those? Water and Na plus will not react because that would just come back into a strong base, and then they just separate again. But water and C2H3O2 absolutely can. This is a weak acid, so its K values is pretty low, and it's likely to reassociate when water is available. So it's going to grab off one of those hydrogens and turn back into the weak acid, and then my water is now going to be left with OHs. And since my hydroxide concentration is now higher, that makes my pH higher as well. Giving a hydrolysis reaction or being able to pick out the hydrolysis reaction from a multiple choice question is a good reasoning or rationale behind why an acid-base reaction doesn't have the pH that is 7. So that would be an acidic situation. Another one would be hydrolysis of NH3. But I guess for doing hydrolysis, it would be NH4 plus. And so the fact that NH4 plus has the ability to react there with the water can give its hydrogen away, and that's going to cause it to turn back into the weak base ammonia and leave water with an extra hydrogen attached to it, and so that puts our pH below 7.
So like, what's the correct wording if you were to explain why one is like a weak acid and maybe not so good?
Why something's
Like,
an
if
acid
you're
or a
asked
base?
to explain,
Oh, you mean like the solution?
yeah.
Like giving an equation like this, saying that the water and the ion would associate and create hydroxide or create hydrogen would be plenty. If you could give them this equation, I really feel like that's showing them that you know what you're talking about. They want to give you the points.
So is hydrolysis, does it always have to be reassociation? Can it just be like the initial equation? Like that NH4 one, it's just like the first equation. Or did that start off as NH3? And then reassociated?
It could go either way. Hydrolysis is going to happen at any time you have an ion that is part of a weak base or a weak acid, the conjugate of a weak base or the conjugate of a weak acid. Now, how those get into solution could happen a lot of different ways. It could happen from an acid-base reaction. It could also happen because you put a salt, like I could put ammonium chloride and just dissolve that in water. And if I just took ammonium chloride off my shelf and dissolved that in water, it's going to react with the water and form a slightly acidic solution. What? Okay, so there's 2 ways. We call those salt solutions. And so you could put a salt, which is just any ionic compound, in there, or you could do an acid-base reaction. And that's why you kind of have to, anytime you do an acid-base reaction, think about what's going to react first. Fine. No, you're fine. And then what's left over second. Kara, did that get your question answered?
I just know that like when you're like on FRQs and stuff and you look at the answer keys, their wording is like really, really specific and like references like conjugate acid and conjugate bases, and I just like didn't know how to like almost like formulate like an answer.
And if you're looking for, well, the thing is, it's hard for me to, there's the way they write the test, there's no way you can just like memorize answers and say it that way. So I just want to make sure that you try to explain it the best you can. But what's happening here is the conjugate base reacts with water to form hydroxide. But really, giving the equation or saying that would both, I think, get you the points.
Okay.
Thanks.
So could NH3 react with water to form hydroxide?
When NH3 is in water, it's going to reach equilibrium, so a small amount of your NH3 will take. And if we were to talk about this reaction, this is what it would do in your solution. Do you need me?
No, I just came and filled it.
That-
to clean up bookcase.
That was a very little bit.
Yeah, I know.
Okay. That's okay. We're recording it. But NH3 is a weak base, so you would anticipate NH3 causing your solution to become basic. And so the reason that your solution becomes basic is because when you put that in water, it accepts the hydrogen from the water, and then we have hydroxide left over. I actually don't remember exactly what you asked, but did I answer it?
Yeah.
Okay, super. Other questions? What, Joey?
Okay, so from the same system, they just keep reacting with the products. If the products just keep reacting with the water and they're producing acids and bases, wouldn't they just cancel out?
Well, so this is two different systems, right?
Oh, okay.
I was talking about just a different situation. This is still equilibrium, but this is an equilibrium where, like, let's say I put NH4Cl into water, and the NH4 will react with water and turn it into that. Or a different situation, I start with ammonia. Sorry for the confusion. What other questions?
Are those first two equations, are those also equilibrium?
Yeah, this one is an equilibrium, this one is not. Thanks, I should be better about my double-sided arrow. Because anytime you're using your conjugate acid or conjugate base or a weak acid or a weak base, you're always looking at equilibrium. If there's a strong acid or a strong base involved, it's never equilibrium. Do you want me to say it again? If strong acid or strong base is involved, it's never equilibrium. Essentially, all the rest of them it is.
One of the reviews I was looking at was talking about a titration curve for a polytrinic acid, and I guess I didn't find what the picture was talking about. Could we talk about that a little bit more?
I'd love to talk about that a little more. They have really pulled back on what they expect you to know. But like I said, that situation, I would anticipate them giving you some information, and then you just have to kind of use the information to go with chemistry. But the more you're familiar with it, the better. So a polyprotic acid is going to be an acid that has multiple protons, and in acids, protons are really just hydrogens. So let's say I have H3PO4. It has 3 hydrogens. So when you're looking at a titration curve, you're going to have, 3 different instances where you have different peaks. Essentially 3 different equivalence points that would be happening. So it's going to start fairly acidic because you're H3PO4, and you would have your first peak, let's say that's the first equivalence point, where your H3PO4 loses your first hydrogen. And so when that happens, this is where the bulk of the hydrogen comes from. After this, very little hydrogen dissociates. And so it'll keep going, but there's going to be another equivalence point. Clearly, this is going to be a terrible graph. But just imagine what's the point is nonetheless. Now my H2PO4 is now dissociating, releasing a hydrogen. Sorry, thanks.
Okay, I'm just
No, that's okay. That was good. Wait. 2, okay. I should do a different one because I'm going to run out of space. Should have been a -1. Okay. H3PO4 separates the H plus, makes H2PO4 -1. Obviously, it should have been a -1 and not a -2. And then now this dissociates and turns into hydrogen and HPO4. And then it's going to do it one more time. Okay, so just pretend like this was, a real. And so here now my last one, HPO4 -2 dissociates, and here's my last hydrogen leaves and makes PO4 -3. Yeah. Okay. So imagine that this were more to scale and more appropriately drawn. H3PO4 isn't a strong acid. It's stronger than some of the other ones, but it's not a strong acid. So you're, depending on what it's reacting with, I don't know where, I probably should have drawn my scale a little bit better than I did, but you would see 3 distinct spots where you have 3 distinct equivalence points where you have different reactions that are occurring. Abby, do you remember what the question was, or is that just?
No, it's just one of those references in the book that I did not know about.
If I could pull one up online if you want me to show you a real one.
The book has one. It's the same example you did. I just it just says this is a thing. Is do I just need to know that exists?
Like I said, I would anticipate if this topic were to come up, they would give you some questions that would like, with the background knowledge that of just like how a general titration works, or the idea of that your hydrogens, probably they would ask the idea that your hydrogens are each separately dissociating.
One hydrogen at a time kind of thing.
Yeah, I would guess that's what they'd be getting at with a question like that. Obviously, I'm just guessing, because a common misconception is that this just drops all of its hydrogen right away. Now, this is going to have the largest impact on your pH because this is going to dissociate the most because of that common ion effect that we talked about. Now, when these dissociate, I already have hydrogen in solution. So it's only going to dissociate a little bit more. And this one now, I've still got hydrogen in solution, so it's only going to dissociate a little bit more. And so understanding that concept is what AP wants you to do. Now, how they're going to ask you about it, we can only guess. So if they gave you a weird titration curve, I would anticipate you having just to be able to explain.
How does like the first one disassociating the most, like the second and third one doing it less, how does that like impact like the pH?
Well, because if this is where you dissociate the most, pH is determined by how much hydrogen you have, right?
Yeah.
So this is where the bulk of your hydrogen dissociates.
Okay.
So when that happens, now that's where your pH is occurring. I don't know, because we're talking about it reacting with your NaOH. So it's, or whatever it's reacting with, I guess, if we're doing a titration curve.
Yeah.
I'm trying to like guess at what they would maybe say. But anyway, so let's say we're just talking about dissociations, okay? And not thinking about it in terms of titrations. So if this were dissociating, when you put this in initially, you're going to get the most hydrogen here.
Okay.
It's going to basically be your pH. Now, every time this dissociates a little bit more, it adds a little bit more hydrogen, so your pH is going to go down just a little bit. Remember, hydrogen directly
Like
dictates your
that first
pH.
jump should be more than the second, and the second should be more than the third.
Yeah.
Okay.
Yeah. Other questions?
Are there any polyprotic weak acids that dissolve all of their hydrogens at once?
Every acid will just do one hydrogen at a time.
Are those actually liquid?
This would be your pH. If this is a titration curve, you're always going to have your pH here on the left and the amount of base that's added in this instance, because I started with an acid, the amount of your titrant that's added. Titration curve. You'll have your pH over here. I don't know. I really didn't draw it well, but your titrant that's added would be down here. And so in this instance, it would be a base like NaOH or NH3 or something.
Then the H plus makes H2O the base. The H plus is in all the products. Does that make H2O base? Because you're adding base. You're making a lot of H pluses, but the pH is so.
Well, so that's why I said if we're thinking about it like it's a titration, I'm not talking about a dissociation. So this and this are going to react and they'll make HPO4 and my OH and water, right? And then Na will be left, H2PO4. So one of my hydrogens gets pulled off there, goes with my OH, and then it forms water, right? So because this can continue to dissociate, my NaOH, remember, it's going to react with that and make water and HPO4. And then same thing will happen up there, water and H2O4, or PO4. And then each of these are now conjugate bases and have the ability to reassociate with water. So I'd have to draw a second equation. None of these should be equilibrium, mind you, because they're all reacting with NaOH. So I would have my conjugate bases in each situation could then react with water and then could then pull the hydrogen off and make hydroxide. And that's why your solution is getting more basic. If we're thinking about this as in terms of a titration. Kind of gone back and forth between a titration and just talking in general about how polyprotics work.
changes the pH, then the pH would be getting higher.
And if we're talking about titrants being a base,
If we were releasing H plus, which is an acid, why would the base become?
so it started here as an acid, right? This is an acid. Started off an acid. And in a titration, now I'm adding base to it. So as I add base, very little changes. But once I get enough base to react at my equivalence point, now all of my H3PO4 has all gone, and it's all turned into H2PO4. Now my H2PO4 is going to react with the water and reach equilibrium and cause my hydrogen to go back and become H3PO4 and hydroxide.
So I was doing a little last one, and we were creating H plus.
So we're not doing a titration. It's generally just dissolving. So here, H3PO4 doesn't have anything to react with. It's just on its own. So then my hydrogen dissociates. Okay, what's your question? Should it be an acid or a base?
Because of the H plus.
It's not going to get more or less. Once it dissociates, that's the amount of acid it can have. So here, before I've reacted it with base, it's going to be acidic. But once I start adding base to it, I add base, that base causes it to turn into a conjugate acid, or I'm sorry, conjugate base, excuse me, which then reacts with water, which then makes it basic. And as that continues and continues, does that make sense? Okay. What other questions do you guys have? Go for it.
I have a question, but what's doping?
Doping?
Yeah, isn't it?
Yeah, it might one of my reviews also like referred to that. I don't know, is it gonna come
It's when you, I think it's sometimes the male, sometimes the never covalent bonds. Yeah, never covalence. And it's like you were talking about where you have like a hole, there's an excess or one less electron. Remember, and then like some electron will come and try to fill the hole, and then it'll create another hole, so it increases like the conductivity.
I mean, that's all the thing. I don't typically call it doping, but I mean, that could be. I believe you. And maybe they just got away from using that because now it's got such a negative connotation with all the stuff that happens in sports. But honestly, I could see that being a thing. What'd you say?
It's when you take steroids, if
Right.
you exam, you get 5.
I could see that. Do you have like a particular?
No, it's just like book, and I didn't know it.
Did Wood and Joey talk? Did that make sense? Do you remember talking
I
about
think
that?
it's went very well, so you should probably go for it. I can read from my book. It's like really well in like 3 sentences, so.
Okay. It's a lot of pressure. I don't know if I can explain really well in 3 sentences. We talked about it when we talked about if you make alloys. All right, so let's imagine we have an alloy, right? And so magnesium has a set number of valence electrons, has 2 valence electrons. So if this is an alloy, it's sharing all of those valence electrons amongst all of the other atoms, right? And if we do a alloy, we would switch it to change with a different metal. You might put in chromium or something else in that metal to cause it to have a different.
So, here.
No, it's okay. I mean, You got 3 sentences of explanation. The moral of the story is now we have a different number of electrons. And so as those electrons are flowing, they're basically a gap is created. And so that attracts another electron into it that then creates another gap. And then that attracts another electron into it, creates a gap. You can kind of see where I'm going with that. So when you've now changed your number of electrons that are available, that can increase your conductivity or decrease it, I suppose, depending on how you're changing it. So does that, between our conversation, are you good? Okay. And then I'll get you one.
This is kind of off topic, but should we know all the metals? Like, I think we talked about like 3 or 4 different types of metals that when added to alloys change their properties, and so maybe not.
I don't think you have to know those off the top of your head. If you remember one of the multiple choice questions that we went over in class, they had like the 4 different pictures of the different metals, and they gave you the description. When we added, I think it was chromium, it decreased the likelihood of oxidation because it puts a layer on the outside. So they told you everything they wanted you to know. I think we talked about it in class, so hopefully that helps you be familiar with it, but I think you should just be able to use it.
What about KSP?
Anything, were you here earlier when we talked about KSP?
I don't remember.
Okay, I don't remember either. We talked about that a little bit, so I don't know. Do you have a particular question or?
I guess in terms of how differently like KC.
The biggest difference that we did kind of talk about a little bit between KSP and all the other ones is that you're dissolving a substance in water. And that substance is going to start as a solid. So this is our solid. And so when that separates out, I'm doing a different problem since we kind of did this earlier. When that separates out, this isn't going to have any impact on your equilibrium at all because solids and liquids aren't included in equilibrium. So your KSP is going to be based just on what your products are. And so the concentration of Ba plus 2 and the concentration of Cl minus squared would be your equilibrium expression right here. You just ignore your reactants altogether. So in this instance, if we started with nothing, then I know I'm going to shift it forward to replace that, or make that, I guess. And then remember that whatever your coefficient is here has to be your coefficient there because you still have a stoichiometric relationship. So you end up with x and then 2x. So when you go to plug these in here, x times 2x squared. So now you're either going to be told x, and then you can solve for KSP, or you're going to be told KSP and asked to solve for x. So that's, I guess, KSP in a quick nutshell. Do you have a more particular question, or does that kind of help you? Okay.
Like network covalence, will you be able to like identify like one of those, or will they be like, this is a network covalent, explain why it like has like a high boiling point or something?
I think they would tell you this is network covalent, but SiO2 is one that's they're often used as a network covalent. They would want you to know, or that I think you should know just because they're weird. Graphite probably are good ones to know.
Can we like talk a little bit about like why those happen and how like the shape of those gives them like the properties they have?
Mm-hmm. So what you see there is it's a combination of covalent bonding as well as delocalized electrons. And so you essentially get, I'm sorry that I'm terrible at art, but just kind of go with me. And so you have basically, like you said, I said a combination of the two. And so imagine that you've got your electrons here that can kind of move freely. And you've got electrons here that can also be shared between the two sides. So in a network covalent, because you have both delocalized electrons, it gives you a little bit of an ability to have some metallic properties. You get some covalent bonding. Sorry, that's not what I'm going to say. Yeah, that's true, but conductivity is what I meant to say. You get some conductivity, and it has, whether that's thermal energy or electricity, it has that ability to conduct. It's going to be more likely to break, it's a little more brittle. because you can break it apart in layers. That's why when you write with your pencil, your top layer gets left on your piece of paper. Your next layer gets left on your piece of paper. And so that layer together is pretty strong. The in-between layers are a little bit weaker. Is that good, Abby, or do you have more questions?
Yeah, that's good.
Okay, that's all I got.
Is it like a calculation of the salt?
Like what would be the pH of a salt solution?
Is it very different from hydrolysis?
Well, I mean, we didn't do a calculation with it. We just talked about it, right? So we could. Sure. So do you have a particular one in mind, or should we make one up? Okay. Is it okay?
Working on salt. That's particular.
Okay, so let's say I have a solution. Bye, have a great night.
Okay. I emailed you some stuff regarding tomorrow.
Oh, I saw that.
Okay.
Thank you. And I saw your sub plans because they're on the printer. So
I'll talk to you later.
Bye.
Thanks.
KSP. Okay, sorry. I forgot what I was doing. No, that's not what I'm doing. I'm doing,
Calculating salt solution.
thank you. So I need to give you a salt solution. So let's say it's sodium acetate because I was using acetic acid earlier. So I have a solution of sodium acetate. Let's say it's 0.25 molar solution of sodium acetate. And let's say we want to know the pH of that solution. So far, so good? So the first question you have to ask, since this is, chances are they're not going to tell you, hey, this is a salt solution. Do a hydrolysis problem. Like, you have to be able to recognize this. If that goes into water, if it's a salt solution, you have Na plus in water, and you have C2H3O2 in water. And it's your job to know which of those are going to actually happen. If these two react, they make NaOH and H plus. So that's not going to be my reaction because NaOH is a strong base. So that's just going to dissociate again and leave me back my net ionic equation. I have no reaction. So that's not it. And then when these react, I will get a weak acid. And since my hydrogen is going to leave here, it's also going to leave me with some hydroxide. So far, so good. I should have given you a Ka value.
When you do this problem, can you also just like explain how to convert from Ka to Kb?
I'll have to. Mm-hmm. I kind of, for some reason, think the Ka is for something around 5 times 10 to the negative 8. 1 point.
I don't have one times like that.
No, I think that acetic acid, I don't know why. I just think that it's something else more like
Go through.
Hmm?
Just go through.
So I'm not 100% sure, but we're going to go with that for now. Either way, it's a small number. All right, so that gives me, so one of the things that is beneficial about this problem is they give you the Ka for your weak acid. So it is kind of a clue that, oh, that's probably going to be my acetate, or yeah, the acetate that will react to form your HC2. So then I need to set up an equilibrium problem. I'm going to do an ice table. Initially, I had 0.25 moles, or molarity, excuse me, of that. Since I'm doing equilibrium problems, you always want this to be in molarity, so that's good. This is water. It's a liquid, so it's not going to be involved in my equilibrium expression. And you're assuming initially you had none of those in the reaction, because this is all you did was you just dropped this into some water. So then the reaction has to move forward. Subtract x, add x. So we're assuming if we set this up here, my equation is going to have HC2H3O2 and OH minus C2H3O2. Right? And so if I did this and I set here my Ka value that I was given in my problem, it would be bad, right? Why is that bad? It's a basic solution. I have a base that's reacting. So I have to have a base as far as my K value goes. And give me one of those. So this is where I have to convert. And KW is equal to KA times KB. So if I plug my numbers in, this is 1 times 10 to the negative 14 is equal to 5 times 10 to the negative 8 times KB. What do I get? Somebody do it. What? Okay. Sounds like a winner. So now I got a KB value, 2 times 10 to the negative 7. And now I can go in and I can plug in my information. I've got 0.25 down here. I'm going to go ahead and drop that X because that's a fairly big difference between those two. And then I know this is X and I know this is X. Yeah, well, I'm being lazy. Okay, thanks. So if I take 2 times 10 to the negative 7 times 0.25, what do I get? Some number. So yeah, I probably could. And then we take the square root of both of those. No, because here it's 0.25 minus X, not times X. So I can't cancel it, but I did just drop it anyway because it's not going to make that big of a difference. I'm sorry, Lively, what'd you say? Times 10 to the negative 4th. Okay, so this would be my X, which remember are both of these. So that tells me how much hydroxide we have. So you'll take the negative log now of 2.2 times 10 to the negative 4th. Just going to give me something less. 3.8. You want to do it? Okay. I was just making that number up. So that's my POH, 3.65, you think? Is that what you said, Kristen? All right, we'll just go with it. Okay, so imagine you took negative log. Okay, so at 3.65, and then you do 14 minus 3.65 to get you your pH. What other things would you like me to teach you about? Lauren, and then
What is the situation in ice tables when you use moles instead of water?
you never use moles in an ice table. We used moles because if you remember in acids and bases, sometimes instead of reacting your substance with water, you would react an acid and a base together, like a strong acid or a strong base together. And so initially you need to figure out how many moles of one react with the number of moles of the other. And then with what's left over, you do an ice table. But ice tables will always be in molarity.
Is that the before and after table?
Yes. Anna, did you have a question?
Yeah, there's another off topic one.
Okay.
Can you go over resonance and formal charge?
Yeah.
Are there any like topics that they always ask about that we should most certainly
I'm guessing you're not looking for things like equilibrium. You want something more specific than that?
I mean, yeah, probably. Like it's maybe like a certain type of problem like on the
So you have to keep in mind that this test is only just a couple years old. So we don't really have a lot of alwayses yet. The first year it was way too long, and so they've been fixing it. And the second year it was still pretty long, but much better. And so it's just like each year it's a little different, and I only have a small, tiny bit of data, so I don't think I could tell you in always other than, chemistry. and things like equilibrium and titration reaction, but you know those. So, sorry. Resonance structures. Do you have one off the top of your head you want to talk about, or just want me to make one up? All right, so we used SiO2 a few Lewis structure, or a few times ago, SiO2, and we drew its Lewis structure from that. No, SO2, not SiO2. Do you want me to go through it again, or can I tell you its Lewis structure? Some of you were here that day, but a lot of you were not. Would you like to review on Lewis structures? Like, how do we do them? All right, so then we're going to go with so far so good. This is something that would participate in resonance, because there is nothing about this oxygen that's different than this oxygen. So having a double bond on this one instead of that one doesn't really make sense as far as chemistry goes. So what this atom actually does is it's going to resonate the double bond between the two sides. And so you would want to represent your Lewis structures using both, and not leave myself nearly enough room for this. You would want to show both, and the fact that that electron will actually travel in between the two, creating a double bond on both. Now, I don't foresee them asking you a question just like, do you know which of these is resonance? That's kind of what they're saying they're trying to get away from. So they probably ask some sort of question that's related to it. And I don't know, I can't think of anything off the top of my head that's like, this is the type of question they would ask you. But that's what it is, in case you need to know something resonancy. And formal charge was the other one. Formal charge, I hesitate to tell you, because then everybody wants to use it for everything. And it's just not something that you should use very often. You would use it very sparingly. But if you were given two different Lewis structures and you needed to provide a rationale for why one is more appropriate than the other, formal charge is where you would go. Formal charge asks you to compare the number of valence electrons you have originally to how many you have in a bond. So you subtract those two. So sulfur has how many valence electrons? 6. And then how many does it have in a bond? Well, it's sharing 4 electrons in here, but since it's sharing it, you only count 2 towards sulfur here. And then you have 2 here, and then you have 1 here. So that's 2, 4, 5, minus 5. So its formal charge here is a positive 1. I feel like I did something wrong there.
So if there's 2
I mean, I know I did that right. I'm concerned about my Lewis structure.
if
whatever.
there's a double bond, then that's 2.
So this is 2 electrons. So 1 is counted in this side and 1 is counted on that side. And that's the second set of electrons. So 1's counted there and 1's counted there. What? And then, so there's 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons. So that's how many are bonded versus how many are valence electrons. So my formal charge is +1. The closer you get to 0, the more preferable that is.
So in the event that they say like a random FRQ, draw a Lewis structure for SO2, if you don't draw this resonance structure, will that be wrong?
I would anticipate then saying something like draw the Lewis structure and any resonance structures that apply or something like that. I would guess they'll give you some prompting. Because if they just ask you to draw a Lewis structure, then it gets a lot harder when you go to grade it because they weren't very clear on their
I
question.
have a question about
Oh, I'm sorry that I just erased.
It's okay. In
Whoops.
the one of the books when it talks about resonance forms, it talks about calculating a bond order with that.
Calculating a bond order.
Yeah. And I what is a bond order I don't know.
So what you need, bond order, the idea is kind of understanding difference level of priority, I guess, for single bonds, double bonds, and triple bonds. when you're looking at bond order, you're just talking about like the number of bonds that you would have between your atoms. Do you have like a question there?
I don't know, like in the book, it's like under resonance structure that like calculates the bond order for like the resonance structure it like talked about. I don't know. Seems like a thing.
Right. So where those typically come up is kind of understanding that a double bond does behave a little differently than a single bond, and a triple bond behaves differently than either of those two. And what you're looking at there is the fact that when the oxygen and the sulfur are sharing two pairs of electrons, that's going to be more Coulombic attractions because it has a greater magnitude of charge between the sulfur and the oxygen than when sulfur and oxygen are only sharing one bond. And so the strength of the double bond is stronger than the strength of the single bond.
Okay. I don't know, they do like math with it? Am I going to be expected to do math?
No.
Okay.
Is this a new?
This is the like, it's like the 2016 like Chem Review one. It's like, am I going to like when it does the math, whatever, it like spits out a number. What does that like number mean?
It would be using it to compare to something else and be talking about bond strength.
Okay. So like if it tells me like two different bond orders, is it like the larger the number, the like the more strength of?
Yeah.
Okay.
And I would guess that's where they're going to ask about it. I can't, off the top of my head, think of any question on any of the new tests where they talked about bond order.
Okay.
Okay. I can't. If something comes to me, I will tell you about it. But
Even if you did break like the single bond, wouldn't that like by default break or change the other two bonds, even though they're stronger, because then you've left those electrons?
so you're saying if I broke,
Like in SO2, if you took off the left one only had one sigma bond, if you broke that, wouldn't it have to change the right side? So it had like the proper.
well, if you broke it, that would be in like a chemical reaction, right? And so you would break all of your bonds at the same time, and then you'd rearrange them and make new. Even if you put the S and just the O together, it would still break them apart and then rearrange them in a new way.
And then if you like calculate, if your overall formal charge, like all of them add together, is not zero, then it's like not a real molecule, right?
Right. Well, no. Your overall formal charge has to match the charge of your molecule. So let's say it were like a polyatomic ion, and hydroxide was the one we were using earlier. Your overall,
Okay, yeah.
so they have to match your charge. Most of the time, your molecule's charge would be zero. So most of the time, that's true. Did somebody else have a question over here?
Can I just ask you, like, nothing. Like when you do hybridization, do you just go like sp3d, or do you go like sp3d5?
sp3d.
Okay, yeah, like 1d.
So they say they're not going to ask about d orbitals in hybridization. So I don't know, but it would depend on how many electron domains you have. So if you had SPPPD, that would be 5 electron domains. If you had 6 electron domains, which is technically people out there think is possible, but that's kind of in debates. So you would cause it sp3d2. But the rumor on the street is they're not going that far.
I think I remember you saying you think pseudo-K would be on AP test, right?
Well, I don't know. K definitely would be on the AP test. Being comfortable with the, I don't think so. The reason I'm saying that is because not everybody does the Crystal Violet lab, which is when we did pseudo K and kind of explain that. And if they had an expectation of you knowing that, I would think they give you some sort of background or some sort of explanation to go with that. I would hope. Any other questions? You want to call it a day? Sounds good? All right, awesome. Thank you, guys.